Hello everybody, so in this video we're going to be starting a new topic which is Differential Calculus 1, and you will find it in your textbook as Chapter 9. So you might be asking yourselves, why are we going from Chapter 6 and 7 all the way to Chapter 9? And the reason is that Differential Calculus deals with functions, and functions such as trigonometric functions and polynomial functions with which we are very familiar. So it's a good idea to jump into calculus and wait till we come back to school next year to cover the other topics such as statistics and probability. So without further ado, we're going to begin this topic of differential calculus. And the first thing we're going to take a look at is the learning objectives. So what are they? First of all, we're going to look at the concept of limit. That's something that we're going to study today. Also, the derivative as a gradient or slope function as the rate of change. You might not be familiar with this terminology, but as you advance in the topic, you'll see that all this is quite simple. Finding the derivative of polynomial functions, the derivatives of sine and cosine, and these four topics we will be covering today. In further videos, we'll be looking at the relationship between the graphs of a function, first derivative and second derivative, identifying where functions are increasing or decreasing, different tests for maximum, minimum, and inflection points, kinematic problems, that means physics, problems of motion, involving displacement, velocity, and acceleration, and finally, how to find the equation of a tangent or a normal at a given point. So like I said, maybe you're not familiar with some of this terminology, but as we advance in the topic, you will see that all of this is quite simple. Okay, so in the next slide, you're going to look at a couple of graphs that compare two situations. So on the left, you have a curve and a line going through 2 points, in this case 4, 2 and 10, 4.25. So since this is a distance over time graph, the slope of this line that we see here going through those 2 points would represent an average velocity in that time interval. So from t equals 4 to t equals 10 seconds, you have an average velocity of 0.375 meters per second. So what calculus deals with is with what we see here on the right. It's the same graph, the same line, but in this case, we have a point which is 7.3875 and a line that is tangent to that point. So the slope of this line at that point of tangency would give us something called the instantaneous velocity. So if we calculate the slope of this line, we would get 0.25 meters per second. What does that mean? That means at that very instant, when time was equal to 7 seconds in this case, the instantaneous velocity would be 0.25 meters per second, represented by the slope of this tangent line. So that is what calculus deals with. Okay, so now we jump straight into 9.1, which is limits of functions. That's the topic. Example 9.1, evaluate the limit as n approaches infinity of 1/2 to the power of n by using your GDC, your graphing display calculator, to analyze the behavior of the function f of x equals 1/2 to the power of x for large positive x values. So what a limit implies is what happens as the variable in the function approaches another value, right? So what if, in this case, n, they say what is the limit of 1/2 to the power of n as n approaches infinity? So that means in the case of f of x equals 1/2 to the power of x, what happens when x has very high value? So what happens when you have 1/2 to the power, say, of 10? Well, this is the same as 1 divided by 2 to the 10, right? If you have 1/2 to the power of 100, that equals 1 divided by 2 to the power of 100. So obviously, the limit as n approaches infinity for 1/2 to the power of n is 0, because these values are getting closer and closer to 0. If you divide 1 by larger and larger numbers, you get closer and closer to 0. So we're going to see that in the next slide where there is a graph. So let's move on to the next slide. And we can see here precisely the graph of 1/2 to the power of x. So you can put this into your graphing calculator, and you will get a function that is definitely getting smaller and smaller and smaller as x increases. So as x, right, because here we're talking about terms of x, but it's the same thing, right? X or n, it's just a variable. So as x approaches infinity, f of x, or the graph, as you can see here, gets closer and closer to 0. So for example, in this table, we see what happens when, say, x is to the power of 13. So if you have 1/2 to the power of 13, you get 1.22070313, and this means times 10 to the power of -4. So that means, what that means is that you get 0.00, one more 0, 1, 2, 2, etc. Right? So this is obviously closer and closer to absolute 0. All right, so next we are on example 9.2, and here they ask us to find the value of the following two limits by using your graphing display calculator to analyze the graph of the relevant function. All right, so the function is sine of x over x. Here they're asking for the limit as x approaches 0. So notice that in this case, it's not the limit as x approaches infinity. But what happens if we plug in 0 into sine of x over x? We would get sine of 0 over 0. And obviously this is undefined, right? This is undefined. Therefore, we cannot really find out what the value of the function is as x approaches 0. In this case, we get the same thing, because the limit as x approaches 0 of cosine of x minus 1 over x is the same as plugging in cosine of 0, plugging in 0 minus 1 over 0. And this is also going to be undefined because we cannot divide by 0. So there's no way we can know what these limits equal simply by plugging in the number 0. So what we do is look at the graphs. So that's what we're going to do next. So in the next slide, you will find the graph for sine of x over x. So this is what you would see in your graphing display calculator. That when x is 0, you see a big hole in the graph. That just means it's undefined there. But we can analyze this in a different way. What happens when you approach 0, the value 0 for x, from the left and from the right? What happens to y? Well, let's look at y. As you can see, as you approach 0 for x, y gets closer and closer to 1. So that means that the limit, we would say this, that the limit as x approaches 0 of sine of x over x is 1. Okay, so let's take a look at the next slide and see what happens in the case of cosine of x minus 1 over x. So let's take a look at that. And we can see this situation here. So there's the graph right there of cosine of x minus 1 divided by x. So notice that we have this here. It goes through or close to 0, 0. Notice that at exactly 0, it's undefined. That's why you see an error here in the table. But what happens as you approach 0 as an x value from the left or from the right? So here they're approaching it from the left, and these are the results we get. This is where they approach it from the right, And these are the results you get. Now notice that all of these are close to 0. 0 0.115, 0 0.1, 0 0.005. So the closer you get to actual 0 for x, you get closer and closer to 0 for y. That's why you can conclude that therefore the limit as x approaches 0 of cosine of x minus 1 over x is 0. All right, so the next example is 9.3, and it says find the limit as x approaches 0 of 1 over x squared if it exists. So what happens if we plug in 0 here? We're going to get 1 over 0 squared, which is 1 over 0, and again, this is undefined. But like we said before, there's another way of doing it, which is testing values approaching 0. So let's say that we have 0. What happens if we approach it from the left or we approach it from the right? What happens to the graph? So we're not going to plug in values. We're just going to take a look at the graph, and that's in the next slide. So let's do that. Let's just go to the next slide. And we can see the graph here to the right. Notice that as x approaches 0 from the left or from the right, the function just goes up into infinity, right? Whether it's from the left or from the right, you can see the function increasing to infinity. So that means that 0 is a vertical asymptote. In other words, we can conclude that the limit as x approaches 0 of 1 over x squared does not exist. Why is that? Well, because of the definition of limit. In order for a limit to exist, it has to converge to a value L, right? So we can see that here. Unless it converges to a value, you will not have a limit. So in the next slide, what you're going to see is a recap from a previous section, in this case, section 2.2, which talks about the end behavior of rational functions. So if you grab a rational function like this one, that you have here to the right, and you calculate the limit as x approaches infinity for an expression like 3x squared plus 5x minus 1 over 2x squared plus 1, this is going to give you 3 halves. So 3 halves is actually a horizontal asymptote. So these limits to infinity actually reveal what the horizontal asymptotes of functions might be. We can see in the graph, this would be the graph here in red of the polynomial function, and the black line here, y equals 3 halves, is the horizontal asymptote of said graph. So after those examples, you're going to find exercise 9.1. Please work on the questions from this section. Very well, so let us continue with topic 9.2, the derivative of a function, basic rules, and facts. So the first thing they talk about is tangent lines and the gradient or slope of a curve. So basically, just so you understand the term derivative, if I have a function like this one here, you see the one on the left, this curve, which is obviously a parabola, the derivative at a given point, like say this one, would give us the slope of the tangent line. So this is a tangent line at that maximum. So notice how the slope of this line here is definitely equal to 0. And this is a trick we can use to actually find the maximum or the minimum of a curve. By finding the derivative and equaling it to 0, we can find the points on that graph where there is a maximum or a minimum. In the next graph, you see a tangent line on this point, and this tangent line is going down. That means that the slope of this thing would be negative, right? So this would be a negative slope. So let's suppose this blue line represents the path of a certain particle, and that this is a distance over time graph. So this tangent here would give us the instantaneous rate of change at this given point, and it would tell us that at that point in time, the velocity was negative. Of course, if we knew what the function itself was, I mean, algebraically, if we had the formula, we could find the derivative and then consequently find the slope of the line at this point, and therefore the instantaneous rate of change at that point. Then in the next graph, we have another case where there's a point on this graph and the line of tangency to that point. Notice that this line is going up and it's very steep. That tells us that the slope is positive. So you have a positive n, a positive slope for this line, meaning that the instantaneous rate of change here is positive, right? So if this is also represented the motion of a particle in a distance time graph, it would tell us that at this point here, the instantaneous rate of change, or the velocity in the case of a distance time graph, would be very steep, meaning that it is increasing at that point in time. So in the next slide, we can see precisely that situation that I was talking about. Here we have a curve that represents the path of a certain particle. That's the blue line. And this is a distance over time graph. So we have a distance over time graph. So let's suppose we grab a certain point on the graph, let's say 5 seconds. So we see that at 5 seconds, the distance traveled was 3 at that time interval. But what was the instantaneous velocity at that point? Notice that if I use 5, 3 and I subtract it from 0, and I'm going to get, I would get something that would be an average. But what would be the instantaneous velocity at that point? So the instantaneous velocity would actually be the slope of the tangent. You can see the tangent line here going through the point 5, 3. That's the point of tangency, and this is a line just touching that point, therefore being tangent to the curve at 5, 3. So what would be the instantaneous rate of change? It would be the slope of that curve. Notice that we have a rise of 4 and a run of 6. So we would say then that the slope would equal, remember that it's rise over run, right? Or difference in y over difference in x. So this would be then rise is 4 and run is 6. And then we can divide these two by 2 and we get 2/3. So it's going to be 2/3 meters per second. So we can conclude that at exactly 5 seconds, the instantaneous rate of change of this particle was 2/3 meters per second. So the instantaneous rate of change here is an instantaneous velocity. Okay, so on previous slides, we've been looking at a geometric method of finding the derivative at a given point. In other words, the slope of the line at a point of tangency. So if we can draw a line physically tangent to the graph at that point, we can find the slope of that line, and that would give us the instantaneous rate of change at that point. But how about another method? How about a method that is algebraic? So a French mathematician, Fermat, he came up with one method long time ago, more than 4 centuries ago. And it's based on the following principle. So if we want to find the slope of a line, we definitely need 2 points. That's what we've always done, right? If you have 2 points, then you know that all you have to do is divide the difference in y over the difference in x, and you're going to get the slope of that line. And that's what we have here precisely on this first graph to the left. So we have 2 points. This is one point, and this is the other point. And everything is going to make sense as soon as I explain one thing. So let's suppose that this line here, this coordinate, is just x, right? So if this is the x coordinate, this point would be then x, comma, f of x, as you see here, right? That would be that point P. This is just x and f of x, right? So this is regardless of what the function is. then here would be the other x coordinate. But instead of calling it x2 or x prime or something like that, we're going to take into account this distance h between the two x coordinates. So taking into consideration h, this coordinate here would be x plus h, right? So this is x plus h. Therefore, this point up here, point Q, would be x plus h, comma, f of x plus h, f of x plus h. So notice that if we wanted to find the slope of that line, and this is called a second line because it's going through the graph a couple times, and it's not tangent at any point. So the slope of this line here, in this first example to the left, would be difference in y, which would be f of x plus h, minus f of x, right? This here minus this there. That divided by the distance. Normally we'd say x1 minus x2, but if we do that, we're just going to get h, which is this distance here. So notice that this is a right triangle, and when you calculate the slope of a line, as you know, you're doing the ratio of a right triangle. Okay. So on this other graph to the right, we have exactly the same situation. The only difference is that this h is now a bit smaller. You see that? It's still going to be that the difference in y is f of x plus h minus f of x, and that the difference in x is h, only that the distance h is getting smaller. Okay? So what we're doing here, and this is what probably Fermat was thinking, is how do I draw a second line that is closer and closer so that I actually find the slope of a tangent and not the slope of a secant, because for the slope of a secant I need 2 points necessarily, right? I need 2 points necessarily. So let's go to the next slide. And in the next slide we see that first of all, to the left, we have the same situation again, right? A second line and 2 points. The same 2 points, we're naming them the same, only that h, the distance h, is closer to nothing, right? It's reducing. But we have the difference in y still being f of x plus h minus f of x, and the distance in x still being h. Therefore, again, the slope of this line here would be f of x plus h, x plus h, not h plus h. So f of x plus h minus f of x. That's the difference in y. And the difference in x, we don't have to write x2 minus x1. We just know that that difference is h. So then we arrive to this situation here. You see that? This situation here, where there is only 1 point. 1 point only. So we don't have the reference of 2 points. So what does that mean in terms of limits? Think of it this way. The slope of this line here at the point of tangency would be the same as saying, what's the limit of this function as h approaches 0? So as h gets smaller and smaller, remember that h here had a visible distance. But what if h is really tiny, tiny, tiny here, and closer to 0? What happens to this? What would this equal? What would this slope be? So notice that this is actually the definition, the accepted definition of a derivative, right? The limit as h approaches 0 of f of x plus h minus f of x divided by h. Now, luckily, in SL analysis, we don't have to go too much into theory with the definition of derivative, but if you're interested in this topic, if you're a math geek, you can go and watch the HL video on this same topic. So like I said in the previous slide, there is a definition of derivative, which is the limit as h approaches 0 of f of x plus h minus f of x over h. So if we use this formula, we could find the derivatives of functions. Luckily, we don't have to go into this complicated algebra, but rather we're going to study a shortcut through something called basic differentiation rules. So we're going to talk about the symbology of differentiation and some basic rules that make things quite simple. So the first one says constant rule. Now this means d dx. This just means derivative of what's in here, right? So they say that the derivative of a constant is equal to 0. So remember that a constant is just a number. So if I want to do the derivative of, say, number 3, or any other constant, this is just going to equal 0. Now, why is that? Remember that if you have a graph like y equals 3, that is just a horizontal line that goes through the y-axis at the point y equals 3. And it also has always a slope of 0. So the derivative gives us the slope. So what it's telling us is that for any horizontal line, the slope is equal to 0. So the next one is the most important one. It's called the power rule. And it has to do with how to find the derivative of an expression that has x to the power of something. And it says that the rule is multiply x by n and then keep an exponent that is 1 less than n. And n is a rational number. So it means that n cannot be something other than a rational number. Okay, what's an example of this? Let's suppose you have x squared. They ask you to find the derivative of x squared, or to differentiate x squared. That's the same thing. So that means if you do d dx of x squared, this is going to equal, n is the exponent, so 2 times x to the power of 2 minus 1. Right? So we send the exponent to multiply, and then we subtract 1 from the exponent. And we're going to get 2x. Let's say you had x cubed. So what is the derivative of, say, x cubed? Well, this would be 3x squared. Right? We sent the 3 to multiply the coefficient, and we subtracted 1 from the exponent. So this is the basic differentiation rule that you really need to know, and it's very simple, much easier than finding the derivatives through the concept of limit. Then let's look at something called the sum and difference rule. And what that says really is something as basic as this. Let's suppose you have a function, x squared plus x cubed. And they ask you to find the derivative of that. What this sum or difference rule, so this could be plus minus, says is that you can differentiate these individually. So basically it's the same as adding what we found before, 2x plus 3x squared. So this would just equal 2x, which is the result of differentiating x squared, plus 3x squared, which is a result of differentiating x cubed. Then finally, you have something called the constant multiple rule. Translating that into an example, what it says is that if you have something like, say, 3 times x cubed, then if you want to find the derivative of this, you want to find the derivative of this expression, it would be the same as taking out the constant, so 3 times the derivative of the x cubed. And then this would just equal 3 times 3x squared. Therefore, 9x squared. So these are the basic differentiation rules that you need to know and apply. All right, so now we will work on example 9.4. And it says, for each function, 1, find the derivative using the basic differentiation rules. 2, find the gradient of the graph of the function at the indicated points. And 3, use your GDC to confirm your answers for part 2. So the first thing we have to do is to find the derivative using basic differentiation rules. All right, so they want us to find the derivative of this function here in part A. So we can write it as f prime of x. Now this is just another symbology. This also means derivative of f. Remember that you also have derivative of the function f of x, like this. Or you can say dy dx. This is also another way of writing derivative. And you might say, why all these different notations? Well, it turns out that in the history of calculus, you had two different people discovering it at relatively the same time. We're talking about Isaac Newton, Sir Isaac Newton, and this is his notation. And we also have Leibniz, the German mathematician, with this other type of notation that you see here. In the description of this video, I'm going to give you guys a link to a documentary on the history of calculus. Anyway, the derivative of f then is equal, and I'm going to apply the basic differentiation rule known as the power rule, right? So x cubed would be 3x squared plus 4x, that would be the derivative of this expression here, right? Sending 2 to multiply, subtracting 1 from the exponent, minus 15, right? If you do the derivative of this is x to the 1. 1 times 15 is 15, and 1 minus 1 is 0. X to the 0 is 1. And then when we do the derivative, the constants become 0. So 13, the derivative of that is just 0. So notice that this is the derivative of the cubic function. And that's something you're going to see with derivatives. The derivative is always going to be one order lower than the other function. So this derivative will give me actually the gradient of the graph at any given point. So this would be part 1. For part 2, they want us to actually find the gradients of the graph at these points that you see here. So we have to plug them in the derivative. So if we do it with, say, -3, we plug in the -3 in the derivative, we're going to get 3 times -3 squared plus 4 times -3 minus 15. And if you do the math, this is going to give you 0. That means that the gradient of the function f is 0 at the point x equals -3. How about at x equals 3? So the same thing, plug it into the derivative of the function, and we get 3 times 3 squared plus 4 times 3 minus 15, and this gives us 24. So that means that at x equals 3, the gradient is 24. So I'm going to show you how to verify that using the graphing calculator. So let's bring up the graphing calculator. Okay, so here you see the graphing calculator, and you need to go, of course, to y equals whatever, right? And then plug in the function. So f of x is what you have to plug in, and you plug in, as you can see here, to the right, you can see the function here, and it is x cubed plus 2x squared minus 15x minus 13. So graph that. Let's hit the graph button and see what we get. And there is the function. There is your function. That would be the cubic function, x cubed plus 2x squared minus 15x minus 13. So what we have to do is find the derivatives, right, the slopes of the line at -3. Right, remember that this gave us 0, so we're going to see that in a moment. And also we plugged in 3, and that gave us 24 for the gradient of the tangent. So how do we use the calculator to find those derivatives? What you do is that you click the second function. So click on the second function and then calculate. And there on the list, number 6 says dy over dx. That means derivative. So click on number 6 and you get a cursor, like a butterfly. But we're not going to move the cursor. All we're going to do is type in -3. So if you just type -3, it's going to find the derivative at the point where x equals -3. So let's hit enter. And right here, you see that the cursor moved to x equals -3. Notice that this is 1, 2, 3, -3 here. So at -3, you get that the derivative equals this. But what does that mean? This is the same as saying 1 times 10 to the -6. That's just 0, right? This is 0.000001, right? So that is 0. And you can see that if we draw a tangent line right through there, you're going to get a tangent line with a slope of 0. So let's do the same now, but for x equals 3. So what you do is, again, with the calculator, you go to the second function, and on the trace button, calculate, choice number 6, again, derivative. Now you have to type in 3, click on 3, enter, and the cursor moved to the point where the tangent would be. You see that? Because here we have x equals 3. This is x equals 3. So then if you look at the graph, this would be the y coordinate right here. So 3 comma whatever that y is, 3 comma -13. At that point, you have a derivative that equals 24, like we found before. And what that means is that if you draw a tangent to that point, let's try to draw it. If you draw a tangent to that point, the slope of that line is very steep, as you can see, and it is equal to 24. Okay, so next we have letter B, f of x equals 2x minus 7 squared at the points 2, 9, and 7/2, 0. So this is the same as before. First, they want us to find the derivative. To find the derivative, we will have to expand f of x. So we know that f of x is actually the same as saying 4x squared minus 28x plus 49. We're doing number 1. Therefore, the derivative of f of x will be 8x minus 28. All right, so once we have this, we can test what the gradients will be at these 2 points, at x equals 2 and at x equals 7/2. So let's test the gradient of f of x at x equals 2. That's going to be 8 times 2 minus 28. And this gives us -12. Therefore, the gradient at x equals 2 for this function here should be -12. That's the gradient of the tangent at that point at x equals 2. So for the other one, the other value would be 7/2. So let's do the derivative and plug in 7/2. That's going to be 8 times 7/2 minus 28. And this will give 0. Okay, so it means that the tangent of the graph at x equals 7/2 is 0. So we're going to discover whether this is a maximum or a minimum at x equals 7/2. Okay, so let's go to the graphing calculator. So again, the first thing we're going to do is plug in the function, right? So it was 4x squared minus 28x plus 49. And then we graph that. So that would be the graph of the quadratic function, 4x squared minus 28x plus 49. So what we're going to do next then is find the derivative at the points x equals 2 and x equals 7/2. So we do that with second and calculate. And number 6, dy over dx, the derivative. And let's say at point x equals 2, so we type 2 and just hit enter. So there we go. The same result, right? At x equals 2, which we have right there, this is 2 here. This would be the y, which is 9, as we can see here. And then by plugging in 2 in the derivative, we also got negative 12. And that is, again, the gradient of the tangent at that point. So more or less a line that goes through there, obviously with a steep negative slope. Okay, so let's check out now the derivative for 7/2. So we have to go back to the calculator. And I would recommend you just go back to the Y screen, hit enter again, graph, and then second, calculate. And number 6, and just type in 7/2. So that's 7 divided by 2, 7/2. Let's hit enter, and there we go. So at 7/2, the derivative is 0. As we witnessed before, we got 0 there as well. Notice that at 7/2, which is right here, 3.5, we have a horizontal tangent, which means that the derivative is 0. In this case, it is a minimum. Okay, so now we are going to do letter C, which says f of x equals 3 square root of x minus 6. And we are going to do the same thing for the points 4, 0 and 9, 3. So notice that we can rewrite f of x as 3 times x to the 1/2 minus 6. Recall that if you have square root of x in exponential form, that's going to be x to the 1/2. Just like if you have cubic root of x, that would be x to the 1/3, and so forth. So we have to find the derivative of this expression here. Okay, so the derivative of that we can find simply by applying the power rule. So send this to multiply and subtract 1. So we're going to get 3/2 x to the power of negative 1/2. Why? Because 1 minus 1/2, I'm sorry, 1/2 minus 1 is negative 1/2. So notice that this is the same as 3 over 2 times square root of x. Therefore, if I want to test these points to see what the gradient will be, just plug them into the derivative, right? So we have to plug in 4. That's what I'm going to do here, 4. Plug in 4 into the derivative, and we're going to get 3 over 2 square root of 4, and this will give us 3/4. So that will be the gradient of the line at x equals 4. We want to find the gradient of the line at x equals 9, so this is going to be 3 over 2 times square root of 9, and this will end up being 1/2. Therefore, the gradient at x equals 9 would be 1/2. Now, you still have to verify this on the calculator, but I'll leave that to you guys as an exercise. Okay, very well. So now we are on letter D, and this is a polynomial. The only thing is that it has a bunch of coefficients that are fractional, but don't let that scare you. The same rules apply, right? So let's find the derivative. The derivative of this would then be, bring down the 4. So 4 times x is 4x divided by 4 is 1. So we don't even bother writing a coefficient because it's just 1. So x to the 3x cubed minus 9/2 x squared minus 4x plus 15/2. This last term would just be 0, right? So 15/2 here. Therefore, let's find the gradients of the graph at those points. So plug in to the derivative 5, and we're just going to get there 0. So that means that at x equals 5, you're going to get a horizontal tangent. And then if you do the same for 0, plug it into the derivative, you are going to get something like 15/2. And that means that this is the gradient, again, at x equals 0. I'll let you guys do the verification on the calculator on your own. Very well, so now we are on example 9.5, and it says the curve y equals ax cubed plus 7x squared minus 8x minus 5 has a turning point at the point where x equals negative 2. determine the value of A. So what is a turning point? Let's say you have a graph and it looks like this, more or less. You would have two turning points here. This would be one turning point, and this is another one. So turning points are parts of the graph. So if this is f of x, if this is f of x, for these turning points, the derivative is equal to 0. So basically they're saying plug in 3 into the derivative and solve for a. Okay, so if we want to find the derivative of y, y is equal to ax cubed plus 7x squared minus 8x minus 5. So the derivative of that, we're using Leibniz's notation, would equal, and we just use, again, the power rule. So this will just be 3a x squared plus 14x minus 8. Okay, so once we have this, we know that there is a turning point at x equals -2. So that means that if we plug in -2, this should equal 0. So 3a times -2 squared plus 14 times -2 minus 8 should equal 0. Therefore, we get 4 here, so times 3, 12. 12a minus 28 minus 8 equals 0. So we get that 12a equals 36. Therefore, a is equal to 3. And that would be the solution. Okay, so next is example 9.6, and it says boiling water is poured into a cup. The temperature of the water in degrees Celsius C after T minutes is given by C equals 19 plus 182 over T to the power of 3 halves for T greater than or equal to 1 minute. Letter A, find the average rate of change of the temperature from T equals 2 to T equals 6. Letter B, find the rate of change of the temperature at the instant when T equals 4. So for letter A, they want us to find an average. So an average rate of change is going to be the slope of the line between the 2 points where they want us to find that average. So notice that we have 2 points, right? One where T equals 2 and the other one where T equals 0. So we have to find the temperature at those 2 points. So the temperature for time equals 2 seconds, or 2 minutes, I should say, 2 minutes, is equal to 83.35 degrees Celsius. And when time equals 6, the temperature would be then 31.38. So the average rate of change will be the slope of the line between those 2 points. And that's just going to be difference in temperature divided by difference in time. So that would be then 83.35 minus 31.38 divided by 2 minus 6. So we have to do it in the same order. Always remember that's very important. So this is going to give us negative 12.9, which we can round to negative 13.0. And because it's a rate, degrees Celsius per minute. Not M, it's got to be MIN because we're talking about minutes. Okay, so it's 13.0 degrees Celsius per minute. That means that the temperature is decreasing, which makes a lot of sense because if you pour boiling water into a cup with time, it's going to get colder and colder. So for part B, they're asking us to find the rate of change at the instant. So they want an instantaneous rate of change. Now remember that when we're talking about instantaneous rates of change, it means that we want to find the derivative. So let's rewrite the formula. The formula is the same as C equals 19 plus 182 times T to the negative 3 halves. I write it this way so I can apply the power rule. So then let's differentiate, but this time not for x, but for t, right? So this would be then the rate of change, or the instantaneous rate of change of the temperature, would equal, derivative of this is 0, so let's do the derivative of this. It's going to be negative 3/2 times 182 times t to the power of negative 3/2 minus 1. And this is going to give us, let's see, what is it? Negative 273 times t to the minus 5/2, right? Because 3/2 minus 1, negative 3/2 minus 1 is negative 5/2. Okay, and this we can rewrite as the rate of change of the temperature being equal to negative 273 divided by the square root of t to the 5. But the question is, what is the instantaneous rate of change when t equals 4? That means that they want to test this for 4. So let's plug in 4 there, and what do we get? If you plug in 4, you're going to get that this is approximately negative 8.53, and because we're talking about rates of change, it's going to be degrees Celsius per minute. Okay, so that would be it for this video. After this example that I just explained, you're going to find exercise 9.2, and obviously you need to do those problems as well. And as usual, if you have any questions, send me an email, and I will collect all your questions and make a video in response. So best of luck to everyone, and God bless.